For case number 3, we'll have the real and repeated eigenvalues. And then we'll try to solve these, diba? Using matrices. So pretend you have this, for example, x prime is equal to 0, negative 1, 3, 2, negative 3, 3, and 2, negative 1, 1. And then x is the variable matrix. So again, what's the first step when you're given something like this? Always
Find the auxiliary equation.
auxiliary equation. What's the purpose of the auxiliary equation? To solve for?
Eigenvalues.
Yes, very good. So for the eigenvalue. So in this case, you'll notice that when you get the determinant of this auxiliary equation, the auxiliary matrix, you'll get this one, 2, and then negative 2 repeated. So this one here is a case number 1 combined with a repeated. So may case 3 tayo. This is your case 1. And then because of this is your case number 3. Okay, because of the repeated. So how do we deal with that? So typically for case number 1, you already know. So you substitute that in. What's this one? The characteristic equation, yeah? So just plug in when m is equal to 2. So negative 2, negative 1, 3, 2, negative 3 minus 2. So that becomes negative 5 and so on. So you'll notice that you'll have 5 different equations. And then when you solve for the C's, you'll end up with 1, 1, 1. So that's okay. I hope this is not a problem. Now, for m is equal to negative 2, for the first time, let's try to plug it in. Now, you'll notice that in this case, how will we do this? Look at this. The first, the second, and the third lines are the same. So we can only get one equation that's distinct. So how do we deal with that? What I do is, okay, let's deal with the first one. 2c1 minus c2 plus c3 is equal to 0. So this is what you have, right? Now from this, I try isolating C2 because for me, it's easy to isolate C2. And typically what I isolate, by the way, is C2. So if I isolate C2, I'll get 2C1 plus 3C3. Some of you might ask, is it okay to isolate C1? Yeah, it's okay. Is it okay to isolate C3? It's okay. It's up to you. But typically, I isolate C2 so that my C1, look at this. The one on top is C1. Isn't it that the second line, this line here, is actually my C2, isn't it? So you have the C1, you have the C2, and you have the C3. C2 is represented by 2C1 plus 3C3. So what's the reason why I'm doing this? So that the C2 is an expression as opposed to just C2. And then what I isolated is the C2 so that I can assume either C1 or C3, the extremes, the top or the bottom. So look at this. If C1 is 0 and C3 is 1, what is C2? Diba? 2 times 0 plus 3 times 1. Oh, okay. I'll get 3. You understand? Whereas if C1 is 1 and C3 is 0, so 2 times 1 is 2, and then this becomes 0, so 1, 2, and 0. My question is, you have 2 different answers. Are they factors of each other? Or are they parang multipliers lang? May multiplier lang ba? What do I mean by that? If this is 1, 2, 0, the other one is 2, 4, 0. The other one is 3, 6, 0. Hindi, di ba? They are distinct. And then they're not factors. So that means for this one, we were able to obtain already 2 distinct solutions. Isn't it that since this has 3 eigenvalues, I should have 3 answers? This is your first answer from case 1. For case 2, this will actually, case 3, this will actually be your two answers already. So this one or this one, please take note of this. Since neither eigenvector, this is the eigenvector, again, the eigenvalue is this. Since neither eigenvector C is a constant multiple of the other, we have found two linearly independent solutions. So meaning, if I ask you what's the solution, the answer will be this one plus the first and the second. And then isn't it that since both of them came from -2 na m, the e will be -2 for both of them. So the final answer will be this one, the one in red. So let's go back. Some of you might ask, sir, is it okay to assume C is equal to 0, C1 or C3? Yes. Why is it okay to assume 1 and 1? It's okay also. But the thing is, we would want to have as much as possible, the easiest solution. The easiest possible solution. So we'll try to make one of them 0 immediately. Anyway, if this is 0, you know that this will not be 0, this will not be 0. You will not have a column that is composed of entirely 0. You know that the Wronskian, just by looking at the line, will not be 0. Now, when you combine them, that's when we test if the combination becomes all 0. In this case, when we check, the Wronskian is non-zero. So that means truly the solutions are linearly independent. Let's have another one here. 1, 2, -1. Yeah, 0, 1, 1, 0, 0, 2. Okay. Now, solving for the auxiliary equation, the roots of the auxiliary equation. So you'll get 3 eigenvalues, 2, 1, 1. So again, you have a combination of case 1 and case 3. Okay. So with this, let's try. For m equals 2, the characteristic equation would be this one. So typically like 2. I look at the one on top. 1 minus 2 is -1, 2 -1. 0, 1 minus 2 is -1 also. 1, 0, 0, 0. So you'll notice at the bottom you have 0, 0, 0. So you'll get two distinct solutions only. So -C1 plus 2C2. Okay. -C2 plus C3 is 0. So that means C2 and C3 are equal. Okay, if C2 and C3 are equal, just plug it in here, and you'll be able to get a relationship between, let's just say, C1 and C3, diba? So if C3 is 1, of course, C2 would be 1 also, right? And then plug it in here to solve for C1. So you'd be able to get 1, 1, 1. So just put that there. That's one of the solutions already. Now, let's go to the next one. If m is equal to 1 for the first time, okay, just plug 1 in this, and then you'd be able to get 0 to -1, 0, 0, 1, 0, 0, 1. Again, okay, you have two distinct lines only. So from this, you get 2C2 minus C3 is equal to 0, and C3 is equal to 0. Now, where did I get C2 is equal to 0? Because if C3 is equal to 0, you have to take note that 2C2 minus C3 is equal to 0. If C3 is a real 0, plugging that in there, you'll be able to get C2 is equal to 0. So the two ones are real zeros. Silang dalawa. C1 is arbitrary. It can be any value because it did not appear in any of the equations. I will assume C1 to be 1, as you said last time. You can never assume C1 to be 0. Bakit? If C1 is 0, the whole column becomes 0 already. That means the Wronskian determinant will already be equal to 0. So linearly dependent solutions. We cannot have that. So let's assume C1 is 1. And then let's just say the eigenvector that I obtained here, K is 1, 0, 0. Okay, plug that in. So x2, which is solution from the second root, C2, 1, 0, 0, e to the t. Now, Some of you might ask, sir, why is it that this one, isa lang nakuha natin? In the other example, we were able to obtain this. Diba? Because in this case, all three C's appeared. Can you follow? All three of them, C1, C2, C3. And I was able to get two separate eigenvectors that are linearly independent. Whereas in this case, only C2 and C3 appeared in the solution. So I cannot, I cannot do the method I applied to the other one. So what I do here is, for the second round, take note of this, guys. Note that if you are repeating, look at this one. The repetition will obtain at T already. And then the next time, the M1, look at that, M1, this is M2. The next time the M1 repeated, you'll have T squared over 2 as a multiplier. Diba remember that in your differential equations, when it repeats, you will already have the T as a multiplier in front. So let's go back. This one, no questions, right? It's easy. Let's go to the M equals 1, the second time it appeared. So looking back here, 1 minus 1, 0, 2, negative 1, 0, 1 minus 1 is 0, 1, 0, 0, 2 minus 1 is 1. So you're able to obtain this. Some of you might ask, isn't this the same as that? Yes, exactly. Exactly the same. So if it's exactly the same, you won't be able to have a distinct solution. Magiging ganito lang. That's why for this one, what we do here is, instead of 0, for the repetition already, for the first time it appeared, equate that to 0. For the repetition, or the second time it appeared, equate that to k. What is the k? Earlier, we have the eigenvector k. The answer resulting, that's 1, 0, 0. So instead of 0, 0, 0, this is equated to 1, 0, 0. So look at the first line. 2p2 minus p3 is equal to 1. P3 is equal to 0. So if P3 is equal to 0, P2 will no longer be 0, unlike earlier. So what is P2? If P3 is equal to 0, P2 is equal to 1/2. Okay? And then P1 never appeared in any of the equations. So if P1 never appeared, P1 is arbitrary. So can you say P1 is equal to 1? Yes. Would it be okay if P1 is equal to 0? It's okay. It's up to you. However, if the Wronskian determinant resulting will be equal to 0, you have to change that. All right. So let's go to how we will write this. As I said, look at this. For M3 is equal to 1, or the second time 1 appeared, take note, what was the K? The eigenvector K, and then the eigenvector P. Okay. So look at this. The third solution is C3. 1, 0, 0. Isn't it that 1, 0, 0 appeared earlier already? So that means the repetition would obtain a T already. Look at that T. And then it's e to the T. And then this one, since it appeared for the first time, this one would be 1, 1/2, 0, T. So what if 1 appeared for another time? That means your solution would be 1, 0, 0, T squared over 2 e to the T, 1, 1/2, 0, T e to the T, and then whatever Q matrix you have. Sige, let's try solving. I'll solve for you a 2x2 matrix. So again, can you please help me with the steps? What is step number 1? So A minus mi equals 0. Okay. So with that, 1 minus m, negative 2, 2, negative 3 minus m. The determinant of this one should be equal to 0. So you'll have 1 minus m, negative 3 minus m, minus negative 4, so plus 4 is equal to 0. So this is negative 3 minus m plus 3m plus m squared plus 4 is equal to 0. So let's fix this. M squared plus 2m plus 1 is equal to 0. So you'll get m plus 1 quantity squared is 0, or -1 appearing twice. So let's go to step number 2. What is step number 2, guys?
Substitute M.
So m is equal to -1 for the first time it appeared. Substitute that in to the characteristic equation. So you'll be able to get 1 minus -1 is 2. -2, 2, and then -2. We'll have C1, C2 is equal to 0. So this one, if you want to write 0, 0, it's okay. That's the proper way actually if it's 0, 0. So 2C1 minus 2C2 is equal to 0, or you can say C1 is C2. So if we let C2 be equal to 1, the resulting C1 is 1. No problem with that. So that means your final answer is X1, capital C1, 1, 1, e to the negative t. This is your first answer. Now, let's go to the second one. We don't have space. For m, -1, the second time it appeared, let's plug it in here. 2, -2, 2, -2, and then let's just say P1, P2. Instead of 0, 0, isn't it that this one should be C1, C2? Am I correct? Kasi it appeared already eh. So 2, -2, 2, -2, P1, P2. What's C1, C2? The resulting C1, C2 earlier is 1, 1, right? So here, the distinct one that you'll get is 2P1 minus 2P2 is equal to 1. So paano to? Walang nag-0. Edi okay lang. Some of you might ask, is it okay if I use 0 in any of them? It's okay. Diba? As I said naman, just try. However, if the Wronskian determinant resulting will be 0, okay, retry another number. So if you ask me, what will I try? If I let P2 be equal to 0, my P1 will be 1/2. Can you follow? So if you ask me, what is my x sub 2? My x sub 2 is capital C2, 1, 1, di ba? Nag-repeat siya eh. 1, 1, t plus 1/2, 0. Both of them has e to the negative t. So what would be the final answer? The final answer is capital C1, 1, 1, e to the negative t, which is this one, plus C2, 1, 1, t plus 1/2, 0, e to the negative e. So that's your second one.